Okay, now suppose we are asked to find the surface area generated by this curve y equals to fx when it is rotated about the x-axis 360 degree. How do we go about finding that surface area? So first, we will try to divide the area under the curve into many strips. Okay, and each of these strips will have a thickness of small change in x. Now what I'm going to do is I'm going to take one of this strip and ask myself, if I rotate this strip 360 degree about the x-axis, what do I get? Now I'm going to exaggerate a little bit. So this is what you are going to get when you rotate that shaded piece about the x-axis 360 degree. Now you will notice that this shape looks somewhat like a circular cone but missing its top. Yeah, you are right. So what we are getting is somewhat a partial or a part of the circular cone. Now if you are able to find the surface area of this part of a circular cone, and then we can do the same for the rest of the strip to find the surface area generated by each of the strips, sum it up, then we are going to get the total surface area generated by this curve y equals to fx. So that is the plan. So let us first try to find the surface area generated by this one strip. Firstly, I need to know what is this. Now if you recall, this is actually part of the curve. And earlier on, we did mention and give it a name called small change in s, where s represents the arc length. So this is a small part of the arc length. Now, how about the radius? Now, you notice that because it is actually part of a circular cone, so there is a radius here. Suppose I call it R1, and then there's another radius here, which is a different value called R2. Now R1 and R2 is different. Then how do I go about finding the surface area which I have shaded in yellow? Now the thing is, if you recall from arc length, we did mention that we are able to generate that small change in s is actually equals to square root of 1 plus small change in y over small change in x whole thing square. Small change in x, okay, if my small change in x is actually very small, meaning this strip is very, very, very thin, so thin that small change in x is almost zero. Now when that happens, then your R1 and R2 are almost equal. Okay, and to the extent when it is so small, we can just assume R1 and R2 to be equal. And if you look at the diagram, it actually corresponds to a y value. So in this case, the surface area of just one strip is 2 pi r. In this case, r is your y, and L multiplied by L. In this case, your L is small change in s. Alright, so this is the formula 2 pi RL to find the surface area of a part of a circular cone. But this is only for one strip. You're going to find the surface area generated by all the other strips and sum it up. Okay, and we're trying to find the limit of this sum when my small change in x actually tends to 0. Now I'm going to replace my small change in s with this, and this is what I'm going to get. Okay, and we know that this is actually equivalent to integrating 2 pi y square root 1 plus dy dx whole thing square dx. And since the integration is with respect to x, the limits here will be the x value. So from a to b. Now, if you watched the video earlier, you will notice that there is actually another formula or another expression for the small change in s. It can also be written this way. Square root of 1 plus small change in x over small change in y holding square multiplied by small change in y. And this expression is valid when your small change in y tends to 0. So this would mean that I could also write down the surface area generated when I rotate this curve about the x-axis using another formula. That is, limit as my small change in y tends to 0. When I sum up 2 pi y small change in s, but this time round I'm going to use this formula, square root 1 plus small change in x over small change in y holding square small change in y. And this is equivalent to saying integrate 2 pi y square root 1 plus dx dy holding square dy. And since I'm integrating with respect to y, my limits must correspond to the y values. So will be from 0 to this point, that is a b comma fb. So to fb. Alright, so there are two formulas to find the surface area generated when a curve is being rotated about the x-axis. Now, which formula to use really depends on the expression. So for example, if it's easy for you to express y and square root of 1 plus dy dx square in terms of x, then naturally I will use this formula. However, if it is difficult, I could only express square root of 1 plus dx dy holding square in terms of y, then I should use this second formula because the integration is in terms of y.